Today we are going to start to discuss a very important problem, and this is regarding the Focault's pendulum. Actually, at present it is well known that our earth is a rotating object. It rotates from west to east about its polar axis, and its period of rotation is 24 hours. It is well known to us. But when this theory was proposed that Earth is an rotating object, definitely as physics is a science of measurement and it is an experimental science, so any theory must be supported by experiment. So there was a need to how to prove that Earth is rotating, and the frame attached with the Earth is a non-inertial rotating frame. These two facts need to be verified experimentally, and it was Focault who at first in 1851 performed an experiment by a pendulum which is now called Focault's pendulum. And by this experiment in 1851 in Paris, Focault at first proved that Earth rotates about its polar axis and its period of rotation is 24 hours. And so the frame attached with this rotating Earth will be a non-inertial rotating frame. So you can say that Focault's pendulum experiment is just an experimental proof of the rotation of the Earth, and the Earth's frame is a non-inertial frame. This was also proven by this Focault's pendulum experiment. So in this lecture we will see how you can say that Earth is rotating about its polar axis by considering the Focault's pendulum experiment. Okay. Actually, this will be just a vast concept, and so for simplicity, I am dividing this lecture in two parts. In first part of the lecture, we will see what is this Focault's pendulum, how it works, and how we can prove this. That mathematical proof in this lecture will be not completed. But we will only write down the equation of motion of the pendulum, and the solution of that very equation of motion will be dealt in the second part of this lecture. Okay. So let us see what is this Focault's pendulum, how this experiment was performed, what was the conclusion from this experiment. Okay. As I have told you that actually Focault's pendulum is just a simple device, and it is used to prove that Earth is rotating, and the frame associated with the Earth is a non-inertial frame. Actually, this Focault's pendulum consists of a very heavy bob, as in case of a simple pendulum, in case of a simple pendulum, our bob is very small, and that small bob is attached to a string of length L, and one of the ends of the string is supported to a rigid support. Similarly, in this case too, just like a simple pendulum, there is a heavy bob. In original experiment of Focault, the mass of the bob was taken 28 kg. This is the mass of the bob in original experiment. Now one can do experiment with different masses, but mass should be very large. And the length of the string of this pendulum is also very large. In original experiment, this was almost 70 meter. And so in this case, actually the time period of this Focault's pendulum was very large, and it was almost equal to 17 seconds. Okay. Now, when this pendulum, you can see I have shown in this figure, this sphere represents a earth, and at a place having latitude lambda above the place on the surface of the earth which is at latitude lambda, let us say this place is A. Above this, at this point, let us say P, this pendulum is suspended from a rigid support. Here there is a rigid support. Okay, and actually this is the bob of this pendulum, and when the bob is aside from the equilibrium position slightly and released, then it makes an oscillation or vibration. Okay, actually when the pendulum is started, it swings in a definite vertical plane. The plane of oscillation is observed to precess around the vertical axis during a period of several hours. And if the pendulum were to be set up at the North Pole, here you can say, I have set up it here in this figure at latitude lambda, but when this lambda will be 90 degree, then you can say that the pendulum has been set up above the North Pole. Then actually when the pendulum is set up at the North Pole of the earth, it may oscillate as a simple pendulum in that condition in a vertical plane, which remains fixed in an inertial frame, or you can say Galilean frame of reference or solar frame of reference. But you know, since the earth under it rotates from west to east with an angular velocity omega, the plane of oscillation of the pendulum will appear to an observer on the surface of the earth to be turning with angular velocity omega in just opposite direction. Okay, if it means you can say that the observer on the surface of the earth finds that this bob is actually turning from east to west. Why he feels that the bob is turning east to west? Because the earth on which the observer is standing, that itself rotates from west to east, so to that observer the pendulum appears to be rotating from east to west. Okay, so you can say that the plane of vibration is rotating in this case. Okay, but if the same experiment will be repeated at the South Pole, then the sense of rotation will be just reverse. In fact, at the South Pole, the observer will observe that the bob is rotating from west to east, that is in anti-clockwise direction. And at the North Pole, he observes that the bob is rotating in clockwise direction. Okay, and for different latitudes, actually the apparent rotation of the plane of oscillation of pendulum due to rotation of the earth will be observed in any latitude except the equator. Actually, you will see later on when we will develop the theory in last, you will find that the period of this rotation will be infinite when the pendulum will be suspended at the equator. Okay, but its time period will be exactly equal to 24 hours when it will be suspended over the North Pole. Okay. In fact, normally the pendulum describes an ellipse, and by making it vibration carefully, the ellipse can be made to appear just approximately as a straight line, so that the pendulum swing in a vertical plane very approximately. Okay. Actually, that is the motion of the bob of the pendulum will be along an ellipse under the various forces acting on it, and we can prove it. So in the theory, first of all, we will show that actually the plane of vibration in which the bob the bob oscillates, that will be a horizontal plane, and in that plane the bob will trace out an ellipse, and approximately when the oscillation will be very small, amplitude of oscillation is very small, that ellipse can be approximated just as a straight line. Okay. So in theory, there will be actually two parts. First of all, we will show that the path traced out by the bob of this Focault pendulum is an ellipse, and then we will see how we can prove that the earth is rotating. Okay, we can prove it, and the frame attached with is a non-inertial frame. Actually, all these facts which I have just explained to you, I have written here for your convenience. So you can pause the video and write down all these things, because in your examination you will need to write these things, particularly in university examination. So if you are going for an university university examination, you must note down these languages where I have actually written all those facts which I have just explained. I am just giving a reading again, but I have already explained these facts. You can see I have written that Focault's pendulum experiment was performed by Focault in 1851. It is the experimental evidence of rotation of the earth about its axis, and the frame attached to it is non-inertial frame. Okay. Now, as I have told you earlier in the construction of this Focault pendulum, that in Focault pendulum a very heavy bob is suspended by means of a long wire similar to a simple pendulum. Thus, if it once vibrated, it consists to vibrate for considerably large time with a large period of almost 17 seconds. Focault took in his experiment a bob of 28 kg, okay, and a wire of 70 meter long. The upper end of the wire is attached to a rigid support in such a way that the pendulum may vibrate with equal freedom in any direction. Okay. Now, how it works? All these things I have already explained, but I am just giving the reading. You can see. When the pendulum is oscillated in the northern hemisphere of the earth, its plane of oscillation rotates from east to west. This is a remarkable fact, and I have already explained it. Or clockwise, as seen from above or by an observer standing on the earth. But if you think that this is due to that the point of support might have turned, that is wrong. Actually, the observer feels this because the earth is rotating. So the observer finds the bob actually turning in opposite direction of the earth rotation. Okay, so I have mentioned it. It is not possible that the point of support might have turned the plane of vibration. The only possibility is that the floor, that is the earth under the pendulum, is rotating. Okay. If such a pendulum is imagined to vibrate at the north pole of the earth, its plane of oscillation will remain fixed in an inertial frame or solar frame, or you can say Galilean frame. Okay. However, the earth under the pendulum is rotating once every 24 hours. Therefore, an observer on the earth will see that the plane of oscillation is turning from east to west opposite to the earth rotation. Okay. Again, I have told you that in normal situation the pendulum describes an ellipse, and by making it vibrate carefully, the ellipse can be made approximate to a straight line so that the pendulum swing in a vertical plane approximately. And all these facts which I have just mentioned, that will be actually proved when we will develop a proper theory for it. And as I have told you earlier that this theory will have two parts, and so I have divided this lecture in two parts too. In first part of the lecture, we will only see what will be the equation of motion of the bob, and after that we will, in second part of the lecture, we will solve that equation. And after solution, you will have a proof of everything, that you will be able to prove that the bob will describe as an ellipse, okay, and the rotation of the earth about its polar axis is 24 hour. All these things will be proven, okay. Now see here, actually here I have considered that from this point A, from a rigid support, this pendulum has been suspended. This is the bob at P at equilibrium position when it has been not displaced, okay. Now this bob at P has been displaced slightly, let us say by an angle gamma, and this is displaced to the position P dashed, okay. And when it will be released, this if the amplitude of oscillation, that is this gamma, is very small, actually in that condition this bob will just oscillate in a horizontal plane, and that horizontal plane has been marked by xy plane, as you can see, okay. Now we consider that the position coordinate of this point P dashed, which is the displaced position of this bob, are x, y, z, okay. Now for writing down the equation of motion of this bob, we will have to decide the forces acting on it. But let us see, if you want to write down this the equation of motion of the bob in the rotating frame of the earth, apart from the real forces, you have to consider the pseudo forces too, because you have learnt in the previous lecture, whenever we write the equation of motion in a non-inertial frame, then we must add the pseudo forces or the fictitious forces acting on the body apart from the real forces. So what are the real forces and pseudo forces acting on this bob? You can see here. See, here the bob is of mass m, so a force of gravity mg, which will be in vertically downward direction, and you can say that this will be minus mg k hat, because this force of gravity is just acting in negative z direction, because the pendulum has been suspended along the z axis, okay. This is one of the real forces acting on our bob. The another real force is this tension T of the string. So there are two real forces. First one is force of gravity mg, and another is tension T, okay. These are the two real forces acting on our bob. And apart from it, you know, in a rotating frame, there will be a fictitious force which is called Coriolis force acting on this bob. There will be centrifugal force, okay. And due to the variation of omega, another force which is equal to d omega by dt cross r times m with negative sign. This also acts on our particle. So there are in general three pseudo forces, okay. So you can see that the forces acting on this bob are what? These forces are mg plus t. Actually these are the vector sum of the two real forces, okay. And minus 2m omega cross v dashed, you know, this is Coriolis force, okay. And minus m omega cross r, this is centrifugal force. All these things you have learnt in the previous lecture. Here actually we consider that omega is constant, and so if omega is constant, the pseudo force defined by this expression minus m d omega by dt cross r, that will be equal to 0. And so I have not considered here in this equation of motion. So this is actually the sum of the real forces. This mg plus t gives the sum of real forces, and the second two terms gives the pseudo forces or fictitious forces acting on our system. And you know, that will be equal to mass of the bob into acceleration of the bob with respect to the rotating frame. And I have denoted that acceleration by the symbol a dash. And already you have learned this idea in the previous lecture. Okay. Now, we will simplify this equation to some extent. This mg plus t, which is actually the total real forces acting on our bob, has been remains at ease. Now, instead of v dash, what is this v dash? V dash is the velocity of the bob with respect to the rotating frame. And in rotating frame, the time derivative operator is denoted by the symbol d dash dt. You have learned it. So instead of v dash, we will write d dash r by dt. You can write it. Okay. Again, the centrifugal force term is at ease. And again, this a dash, when r will be differentiated 2 times with respect to time, by the use of operator d dash dt in rotating frame, then we will get a dash. So instead of a dash, we have written here d2 dash r by dt square. Okay. Now the time derivative may be written in dot symbol. When you differentiate a function 1 time, then you write the 1 dot symbol. If you differentiate it 2 times, you have to write 2 dot symbol. So instead of this d dash r by dt, I have written here r dot. In fact, dot represents the time derivative. So instead of d dash r by dt, you may write r dot. And instead of d2 dash r by dt square, I have written r double dot. Okay. So this is the equation of motion of the bob in vector form. But now let us see something more regarding the different terms in this equation. First of all, we will see what will be this centrifugal force. I have simplified this expression for centrifugal force in the earlier lecture, that when we will take the modulus of m omega cross r, that simply comes out to be m omega square r, as I have actually proven in the earlier lecture. Okay. Now this omega is actually very small. You have seen that the omega, that is angular velocity of the earth, is of the order of 10 to the power minus 5 radian per second. So omega square will be of the order of 10 to the power minus 10. So you can say that this centrifugal force in this case is negligibly small, and in comparison to the other terms, it may be neglected. So for simplicity, we neglect this pseudo force, that is centrifugal force in this case. Okay. And when you will neglect it, what will be then equation of motion? We will simply omit this centrifugal force term, and then our equation of motion will be simply equal to mg plus t, which represents the vector sum of the real forces acting on the bob, minus this Coriolis force 2m omega cross r dash dot, and that is equal to mr double dot. Okay. This is equation of motion of the bob in vector form. But for simplicity and convenience, we will now write down this equation of motion in a scalar form. And if your aim is to write down the equation of motion in a scalar form, you must express all the vectors in this equation 2 in terms of their rectangular components. Okay. So let us write one by one what will be the expression for any vector in this equation 2 in terms of their rectangular components. mr double dot, that can be written as mx double dot I plus my double dot y my double dot j plus mz double dot k. Actually here this x double dot represents the x component of acceleration, y double dot y component of acceleration, and z double dot z component of acceleration. But as we have considered that our bob is vibrating in xy plane, you can see the figure here, the bob has been assumed to be vibrating in this xy plane. And if it is vibrating in xy plane, what will be z? Z will be either constant, or you can say z will be equal to 0. And when z is 0, then its time derivative z dot. Z dot means dz by dt. Since z is 0, so z dot will be 0. Z double dot will be also 0. So here this term mj double dot will vanish. This will be 0. So mr double dot, this will be simply equal to mx double dot I plus my double dot j. Okay, I think you are getting the things. This is a simple concept. Now again you can see the figure. I have shown here that this force of gravity or weight of the bob is acting in vertically downward direction, that is towards the negative z axis. So I have written it is equal to minus mg k hat, minus because this mg is directed in downward direction, and in downward direction the unit vector will be the unit vector of negative z direction, which is minus k hat. Okay, so the x and y components of this vector mg is 0, and it has only z component, and that z component is minus mg. Okay, minus mg. Now the force of tension, if you consider that Tx, Ty and Tz are the x, y and z components of tension, then you can write that T is equal to Txi plus Tyj plus Tzk. This is just a simple idea. And if you consider that our tension vector, this tension makes an angle alpha with x-axis, it makes an angle beta with y-axis, okay, and gamma with z-axis. If you consider, then you know that this cos alpha, cos beta and cos gamma will be called direction cosines of the tension T. Okay, so if T, you assume that tension T makes an angle alpha with x-axis, beta with y-axis and gamma with z-axis. See the figure, I have not marked it here. Actually this will be the direction of x-axis. So this angle is alpha, and with y-axis this makes an angle beta, and this is the direction of y-axis, not x-axis. So this angle will be beta. This angle will be beta. Okay, and this is the direction of x-axis, and with x-axis let us say this makes an angle alpha, and with z-axis it makes an angle gamma. If you consider, then Tx will be T cos alpha, Ty will be T cos beta, and Tz will be T cos gamma. Okay, so in this way we have expressed T in terms of their rectangular components. Now the angular velocity of the earth omega, if omega x, omega y and omega z are its x, y, z components, then you can write omega h, omega xi plus omega yj plus omega zk. But let us see, actually you have also seen earlier in the previous lecture that this omega of the earth, here you can see, lies in yz plane. This is actually y-axis, this is z-axis, and if the bob is at a place whose latitude is lambda, then you have seen in the previous lecture that this angle made by the omega vector with the y-axis, that is with the northward direction, will be also lambda. And so you can say that omega lies in yz plane. Since omega lies in yz plane, so this will be perpendicular to x-axis. And so its x component will be 0 and its y component will be omega cos lambda and z component will be omega sin lambda. You can see that figure. So you can see I have written it here that this omega x is 0, omega y is omega cos lambda and omega z is omega sin lambda. Okay, so omega finally we get this is omega cos lambda I plus omega, sorry, not I but j, and omega sin lambda k. Okay, now the velocity of the bob with respect to the rotating frame, that is r dot. This is velocity of the bob with respect to the rotating frame. So r dot in general will be x dot I plus y dot j plus z dot k. But you know the bob is oscillating in a horizontal plane which is actually xy plane. Okay, xy plane. So in this condition you can say that for any position of the bob during its oscillation, z will be equal to 0 and z is 0, so z dot is 0. I have already mentioned it here, you can see. So r dot will be simply equal to x dot I plus y dot j. Again I am repeating that dot means time derivatives. When you say r dot, that means d dashed r by dt. When you say x dot, that means d dashed x by dt. Okay, and y dot means d dashed y by dt. So these are actually the x dot represents the x component of the bob with respect to the rotating frame, and y dot represents its y component with respect to the rotating frame. Okay. So in this way you can see I have actually expressed all the vectors appearing in this equation 2 in terms of their rectangular components. Now we will evaluate first of all this Coriolis force 2m omega minus 2m omega cross r dot. What will be this? You can see the Coriolis force Fc, this is minus 2m times omega cross r dot. Now this omega cross r dot, this is just the vector product of two vectors, so in determinant form you can write it as this, like this determinant ijk, and here we will write the x component of the first vector omega, and you know the x component of omega is 0, its y component is omega cos lambda and its z component is omega sin lambda. Then we will write in third row the x, y and z component of this vector r dot. You have seen that the x component of r dot is x dot, y component is y dot, but z component is 0. Okay, I hope you have definitely an idea of solving the determinant. So when you will actually solve this determinant, you will see that Fc will be equal to this much. I am not telling the steps, you are able to do that. So Fc is equal to minus 2m times minus omega y dot sin lambda I hat plus omega x dot sin lambda j hat and minus omega x dot cos lambda k hat. Okay, this is actually the Coriolis force. Now you can see what are the x, y and z components of this Coriolis force. Okay, actually the coefficient of I you know is called x component, coefficient of j is called y component and coefficient of k is called z component. So you can see the x component of the Coriolis force, which I have denoted by the symbol Fcx. What will be that? That will be minus 2m times minus omega y dot sine lambda. Now minus minus will be plus. So this is 2m omega sine lambda y dot. Okay. And y component, that is coefficient of j hat, this is denoted by the symbol fcy, and that will be what? That will be minus 2m omega sine lambda x dot. Okay, you can see. And the z component, which is coefficient of this k hat, that will be equal to again 2m omega cos lambda x hat. Okay. After getting the all vectors in our equation of motion in component form, now we are able to write down the equation of motion in component form. So first of all, we will write the equation of motion for x component, then for y component, and then for z component. If your aim is to write down the equation of motion for x component, what you will do? Actually, we will sum up all the x components of the vectors in the LHS, okay, and equate to that to the x component of the vector in RHS. Okay. So in RHS, you know, the x component of vector will be mx double dot, and what will be that? That will be equal to x component of mg plus x component of t plus x component of this Coriolis force. Okay. But you know, x component of mg is 0. So this will be not in our equation. So this will be 0. Okay. X component of t is tx. Okay. So we will write tx. And instead of tx, you can also write t cos alpha. T cos alpha. And x component of this Coriolis force, you can see the x component of Coriolis force is this much. So we will add this 2m omega sine lambda y dot, and then that will be equated to mx double dot. You can see I have done it here. You can see it here. Mx dot, this is the x component of mx double dot. This is x component of mr double dot. And as you have seen that the x component of mg is 0, so I have not written it here. X component of tension, this is t cos lambda. And x component of Coriolis force, this was 2m omega sine lambda y dot. So this is the equation of motion of our bob for x direction. Now we will write the equation of motion for y direction. For this, that we will write my double dot. This is in fact the y component of the vector mr double dot. Okay, and that will be equal to again y component of mg, but you know y component of mg is also 0 because it is directed in z direction. So I have not written it here. Plus y component of tension, that is ty, but you have seen that ty is equal to t cos beta. So I have written here t cos beta. And plus y component of Coriolis force. You can see the y component of Coriolis force is this much. This is minus 2m omega sine lambda x dot. So this will be minus 2m omega sine lambda x dot. Okay. Now write the equation of motion for z component of force or for z direction. That will be mz double dot equal to what? Now in this case, this is actually the z component of the tension, which was t cos gamma. And you can see the z component of mg is not 0. Mg vector you have written, it is equal to minus mgk. So its z component is equal to minus mg. Okay. And plus z component of Coriolis force, which is this much, 2m omega cos lambda x dot. So I have written it here, you can see. So these are the equations of motion in a scalar form or in components form for the bob. Okay. But you have seen earlier that since the bob is rotating in xy plane for a small amplitude, and we are considering a small amplitude, and in that condition you have learnt that z is equal to 0, and when z is 0 you have seen that z dot will be 0, z double dot is also 0. So here instead of this z double dot we may write 0. So LHS of this third equation will be 0, and that will be equal to T cos gamma minus mg plus 2m omega cos lambda x double dot. Okay. So sorry, x dot, not double dot. Okay. And as you have seen that in this figure I have assumed that uh, the coordinates of this point is x, y, z, and the length of this pendulum is L. That is, you can say that this P dash A is equal to PA, and this is equal to L. Okay. Now you can say that with respect to this point P dash, the position vector of this point A will be L. Okay. And the direction cosine of T will be same as that of L. Just with respect to A, the position vector will be AP dashed, and that will be equal to in fact minus L vector. Minus L I have written because this is just in opposite direction of the tension. Okay. Now when you will find the direction cosines, that is cos alpha, what will be that? You can see that will be equal to, this is the alpha is the angle made by this L vector with x-axis. So this if R is, let us say, the position vector, you simply write it as x cos alpha, this will be equal to in fact cos alpha, this will be minus x by L, and cos beta will be equal to minus y by L. Okay. Minus has been taken because the sense is just opposite of tension. And when you will talk about cos gamma, that will be what? You can see this is your gamma, and cos gamma, this will be equal to this L minus Z. This length, you have to take this length. This is L minus Z divided by AP dash, that is L. Cos gamma will be L minus Z by L. So cos alpha is minus x by L, cos gamma beta is what? Cos beta is minus y by L. Let us erase it. Okay. And so at the place of the direction cosines cos alpha, cos beta and cos gamma, you can write cos alpha equal to minus x by L, cos beta minus y by L, and cos gamma L minus Z by L. But as for the case of a small amplitude, the bob is oscillating in xy plane, so we have taken Z equal to 0. And if Z is 0, then this will be simply L by L, which is equal to 1. So cos gamma, this will be just equal to 1. Okay. So in the last equation, that is equation number 5, we will put the value of this cos gamma in this here, which will be actually equal to 1. Then what will be our result? Our result will be T minus mg plus this much equal to 0. Okay. So 0 is equal to t minus mg. Sorry, the page has been turned, but because I am working on this iPad for a long time, so see here. So this is t minus mg plus 2m omega cos lambda x dot. Okay. But this quantity, say, 2m omega cos lambda x dot, this contains omega, which is angular velocity of the earth, and that is very small. You have seen that its value is of the order of 10 to the power minus 5 radian per second. So in comparison to t and mg, this last term may be neglected. Okay, actually this is the vertical component of the Coriolis force. This is component of Coriolis force in z direction, and this Coriolis force will be much smaller due to the presence of this omega here in comparison to t and mg. So when we will see that this omega is very small, this term will be very small compared to the terms t and mg, then we can neglect it. So neglecting this vertical component of Coriolis force here, you can see that 0 will be equal to t minus mg, and so you can simply say that tension T is equal to mg. So T is almost equal to mg. Okay. Now we will substitute at the place of T mg, at the place of cos alpha minus x by L, and at the place of cos beta minus y by L in equation 3 and 4. Oh. And then you will get the final equation of motion of the bob oscillating in this horizontal plane, that is xy plane. So now you can see in LHS there is mx double dot, and in RHS instead of this t we will write mg, and at the place of cos alpha we will write this minus x by L. Okay. So your equation will be mx double dot equal to minus mg times x by L plus this much. Okay. And similarly in equation 4, my double dot will be equal to what? At the place of t again we will write mg, and at the place of cos beta we will write this minus y by L. Okay. So this equation will be my double dot equal to minus mg times y by L minus 2m omega sin lambda x dot. These are the equations of motion of the bob. As I have told you earlier that this is a vast lecture, so I will stop my lecture here without any conclusion. In fact, from this calculation we have not obtained any conclusion, which we have actually explained earlier. Actually all conclusions, all the results will be verified, will be proved in the second part of the lecture by solving these two equations. That is, we will now solve the equations 6 and 7, and after solution of these two equations you will see that the bob will actually trace out an ellipse. Okay, and we will prove that when the pendulum will be suspended over the North Pole, the period of oscillation of the earth will be 24 hours, and when it will be suspended above the equator, that then it will be infinite. So all these facts will be obtained after the solution of these two equations. So definitely after watching this video, you must watch the second part of this video. Only this concept will be completed. So don't forget to watch the second part of the video on the Focault pendulum, which will be just published after the publication of this video. Okay, thank you very much.